Vdovina from Newcastle University. She will speak on fundamental groups of C-W complexes.
Okay, thank you very much. Here. Okay, it really works. Okay, there is such a high tech, of course. So, what is the relation of my talk to this program? So what I remarked in many talks here, people were looking like saying at graphs. I mean, what is the topological ingredient? Yes, not algebraic, but what is the topological ingredient of many presentations? That we have a graph, then what is the universal cover of this graph? It's a tree. And then, of course, so we have this graph gamma, and we look at the fundamental group of gamma. Of course, it acts on its universal cover, and the quotient is just a graph. Yes, this graph. Or if you look at surfaces, we can also consider universal cover over surface, and it's usually some tessellated plane, yes, and the fundamental group of the surface acts on this tessellated plane. And okay, so we can look at the properties of this fundamental group and so on, look at its profinite completions, and maybe then to take some pro-p parts of it. And the question is, what is the right generalization of this picture? Yes, so I would like to start with really citation from Mumford's paper about Mumford surface. So then how it's obtained that there is a P2 which blown up 7 times, and then it's crossing itself at 7 curves, and there are triple points as well. And so maybe even so I was also putting the citation from Lewis Carroll, which I have found in Mumford's paper about maids with grooms. And so what I would like to do maybe first is to show the combinatorics of the Mumford curve, of this really very particular example, but then I will give some definitions and explain how this combinatorics appears. So what is somehow combinatorial picture for the Mumford curve? Surface, of course it's a surface. It's not a curve. Just before my talk we discussed curves and surfaces. So let's take 7 triangles. I will really honestly write all the words. So 6 x0, x2, x3. And x1, x3, x5, x1, x5, x4. Okay, the last one.
The first one is like 2x0?
Yes, exactly. 2x0s. Yes, this is not a contradiction, because it's not like x0, x0 minus 1. It's really x0. This is perfectly fine. So what do we do with those triangles? We take those triangles, then we identify edges with the same labels. So for example, x0, you can see that it appears 3 times. Actually here every letter from x0 till x6 appears exactly 3 times. So there are seven letters, 7 triangles. Yes, so you can already see the pattern. And
We identify you respect the orientation.
respect the orientation. With this orientation is really important. Really, we have to identify them respecting orientation.
These are in relation to the fundamental.
Yes, exactly. Here, in this example, it will be relations in the fundamental group. And why? Because every triangle will become like this. After all those identifications, all vertices of triangles will really go to the same point. And that's why, of course, these are the relations in the fundamental group. And what is, of course, quite nice in this for the Mumford surface, that really we can take this group, we can take its profinite completion, and then there is a complex projective variety such that this profinite completion is exactly the fundamental group of this variety. But it's, of course, it's quite particular case.
And what's the relation with Mumford surface and partition?
So it's exactly so then if we take the relations for, okay, maybe just I have to be more careful. Of course, ask me questions like if for every triangle, yes, we can write down a relation in a group, and it will be a group with seven generators, 7 relations, and we can take the profinite completion of this group. So this profinite completion is exactly the fundamental group of the Mumford surface. Ah, this is it's a good. Just I wanted to give an example to have some interest, because of course it's in the afternoon after lunch. People are sleepy, so so of course it's not. We can talk later, but it's of course not. You cannot see it just from those 2 pictures, but you can.
I'm not sure I understood what this surface, what he means. Does he mean that you take P2 blown up at seven times, and then that maps down to?
So what I would like to say again, it's I can explain later. I just took this small piece of the Mumford of one of the Mumford's papers, because like to understand his.
Is it a quotient of P2 blown up at 7 times? Is that what he means?
It's a quotient. It's
quotient
more difficult. It's more difficult than that. So just an idea. He has
So
some
it's not
more complicated.
It's not a quotient space.
It's a quotient space, but of something more complicated. It's he has some space where the building is a kind of closed fiber of this space, and then there is a group, like the group of this kind, which acts on it. And this is really kind of strange quotient space. So maybe just really I will continue with combinatorics, and then we can discuss the algebra, because I think this paper of Mumford by itself, it's maybe kind of
Sorry, just
topic.
one more
Yes.
question about. So this is a p-adic construction.
Yes, exactly.
But there is also a complex surface, right? when you
Yes,
take this.
yes.
So what happens if you don't take profinite completion? Can you compute the topological fundamental group of that as well?
But the topological fundamental group, just you mean of this complex of the.
Of the Mumford surface. Can you do a computation of that, so it's the topological fundamental group?
But I think it's really very special case where it's really the same. But it's really very special case. So we can look at all the references, but just it's really the same. It's the profinite completion of this discrete group. Okay, so but now I'm going to start with some technicalities. And so I'm going to talk about buildings. And as I said, that it's also the motivation to talk about buildings. In this program, it's because of those Mumford surfaces which really come from buildings. But I'm going to define things in maybe more general context, in such a way that maybe we can maybe think about some generalizations of Mumford surfaces, because like saying from combinatorial and group theoretic point of view, everything looks very similar in a way. So maybe still there are some algebraic generalizations. So first of all, about buildings, they consist of chambers and apartments. And this is, I think, many talks on buildings start with this picture. So what does it mean? It's a graph, it's incidence graph of finite projective plane of order 2. So how you can think about it? So you can think about these blue vertices as points and pink vertices as lines, and there is an edge between, yes, there is an edge between point and line, if and only if this point and line are incident. And then what are the chambers? Chambers are just edges of this graph, yes. And what are the apartments? Apartments are just cycles of length 6. And what are the axioms of the building? Yes, again, to give just first of all to give a flavor what is a building is, it's always, if you take any two chambers, always there is an apartment containing both of them. Okay, so if you take like any two edges and in this graph, you can always find a cycle where they contained. Okay. So, and there is another interpretation of graphs of this kind. It's so-called generalized polygons. So what are those graphs? It's graphs of diameter m and girth 2m. So what is the diameter of a graph? It's the maximal distance between any two vertices in a graph. Okay? And what is the girth? The girth is the length of the shortest cycle. So here the diameter is 3 and the girth is 6. Okay? So this is, of course, this is an example of one-dimensional building. And what is another example? It's just a tree. Yes, it also can be interpreted as one-dimensional building. And now I think we are ready to start with two-dimensional buildings. Okay. So we will talk about geometric realizations of buildings. Like really what is an apartment? Apartment is a tessellated plane. And what are the chambers? Chambers are, okay, here they are triangles, but in fact we can take any hyperbolic planes tessellated by some polygons, and it's perfectly fine as well. Then, yes?
What does tessellated mean?
Ah, okay. Tessellated means just that. So, for example, this is plane tessellated by squares.
So what's the definition?
It's pavement, or I think it's
I don't know. I'm just asking.
it's just your plane, either hyperbolic plane or Euclidean plane, is really covered by one copy of a polygon, which is, okay, for buildings it has to be regular polygon, so, and it has to be really covered. But I never thought about this, but you're absolutely right, because for example what happens for the Euclidean plane, you can cover the Euclidean plane either by triangles or by squares or by hexagons. Yes, so interesting. I just removed a picture from from my talk, not to have too many things. I had like really 3 possible tessellations of the Euclidean plane. So in fact, if you have really Euclidean plane, there are only three possible ways to cover it by triangles, like really with triangles with angles pi by 3, equilateral triangles, then by like such triangles pi by 2, pi by 4, pi by 4, and then 2, 3, 6. Okay, pi by 2, pi by 3, pi by 6. Okay, then just okay, that maybe at least one. Of course, if one tries to draw these tessellations on the board, they never come to. They never match. But I think, okay, from this maybe it's already clear. Yes, what does it mean, the tessellation? It's just you continue this picture till infinity. And then, so this is okay. We clarified what are the apartments are. Now the question is, what are the axioms for the building? So it's really union of such tessellated planes, and there is an axiom that for any 2 chambers, always there is an apartment containing both of them. So of course, if you just consider one tessellated plane, it's an example of a building which is somehow trivial, because of course if you have just one tessellated plane, then you just take 2 triangles and they are contained in the same apartment. But we will work with so-called thick buildings, such that every edge of a triangle is contained in at least 3 triangles. So like if you look locally at your building, every edge is contained in at least 3 triangles. Okay? Yes? Okay. Okay, now I need 2 notions. So the first one, I already explained what we will call a polyhedron. So we just take some set of polygons and then we write some words on the boundary of those polygons, and then we glue them together respecting orientation. And this will be a polyhedron. Okay? So of course we can think about just tetrahedron. Yes, we can think about it as a polyhedron which is obtained from four triangles glued together. Okay? Or we can have maybe less trivial example. For example, if you take 2 such triangles, you take A, B, C, and then you take A, C, B, and you glue them again respecting orientation. Then what you get? You get a torus. And so they somehow, all those vertices of triangles, they go to one vertex on the torus. Okay, so I think about polyhedron, it's already clear. And now what is the link? Another notion which I would like to have, it's a link. Take your favorite polyhedron and any vertex of this polyhedron and then look at a sphere of very small radius with the center at this vertex. Then, so I think I already said that we stay in dimension 2 in this case, that all apartments and chambers are of dimension 2. And the intersection of this sphere with the polyhedron gives you a graph, like one-dimensional object, and this graph will be called the link at this point. So what we do, like we, for example here, what is the link if we have a tetrahedron? Yes, what is the link? It's just a triangle. Okay. But we will need to work with buildings and so on, we will need more complicated graphs as links. For example, what happens here? Yes, if we like really identify here all edges with the same letters respecting orientation, we get a polyhedron with 7 faces, 7 edges. But the question, what is the link? And the link is exactly this graph which I showed before. So the link, that's why it's, again to motivate people to look at links, that for example in this Mumford surface, the link, it's exactly this finite projective plane which appears the link at this of this polyhedron. Okay, and now so let's justify that it's really enough to work with such polyhedra. So what happens? You can think about this particular example. Yes, what happens with the polyhedron if you take its universal cover? If you take its universal cover, we get a building such that all apartments are planes tessellated by equilateral triangles, and all the links of the building are really like this graph. Yes, and the group, yes, which is defined by those generators or in relations, just acts co-compactly, in this case even simply transitively, on the building. Okay, and in general, there is a result of Ballman and Brin that if you take, so their original result is more complicated, but just I adopted it for this particular case, that if we have really polyhedra with links which are generalized polygons, then the universal cover is a building. So of course, if we think only about buildings which have some algebraic nature, like PGL 3K, yes, then of course I think this is not maybe new, like people in algebra knew, there were such facts. But what is good about this theorem, that you don't need to have any algebra a priori. You can have any CW complex which satisfies these conditions on links, that you really have all your links are generalized polygons, and then the universal cover is a building. Okay. But then another question, how to construct such polyhedra? Yes, because still it's not completely clear what is the way to get those words to write on the boundary of disks. Yes, and okay, so it's just a couple of years ago I had, okay, maybe not couple, maybe almost 10 years ago, I had such a notion which of polygonal presentation, which allows you to work with words rather than with geometrical objects. Because what is the technical difficulty? Then of course even somehow from this point of view, the Mumford's example is the easiest one, where you can really think about those 7 triangles, and with 7 triangles you really can play. But what happens if you have some just field of any characteristic and you have many polygons which meet at each edge and so on, then what do you do? And so of course you don't need to read all axioms, but it's just to show that there is some combinatorial notion how to deal with such problems, that we have graphs. Yes, so here in fact this notion, it can be generalized further, but I have found just some version which is maybe not that complicated, but general enough to look at many possible examples. So we have some set of graphs. So in general, we even, of course, in this example, we have just one vertex and one link at it. But in fact, we can have polyhedra with many vertices, and we can have different links at those vertices. And so for those words which have to be written on the boundary of our polygons, there are some restrictions. So the first axiom says that it just has to be that it has to be cyclic. Then the second axiom really tells us that every edge of every graph is realized somewhere in our construction. And the third axiom means that we don't allow multiple edges. Okay, so okay, and then how, if we have this polygonal presentation, it's how to get a polyhedron itself. It's really just like this, that you take a polygon for every cyclic word, you write this word on the boundary of this polygon, and then you do your gluings respecting orientation. But this is really important, that we have to respect the orientations as well, because there are different kind of polygons and polyhedra. So, and then the polyhedron which we get exactly has those graphs which we had on the previous page as links. Okay, so these are some examples which are different from the first which I wrote. So this polyhedron would have 2 vertices and how many, 14 faces and so on. So by the way, this is another example which I like very much, which doesn't, so combinatorially it looks exactly the same as Mumford's example. Okay, how to say exactly the same? We also have 7 triangles, and we have 7 generators in the fundamental group, but just the gluings is different. But the link will be exactly the same. The link will be this finite projective plane of order 2. But the building doesn't come from p-adics. The building comes from Laurent series of a field with 2 elements. And for this case, what is kind of interesting, that the general Mumford's construction works as well. There is some algebraic surface kind of corresponding to this group. But the question, what is fundamental group, it's not clear for me, for example. That's why I would be happy to discuss. It's clear that the profinite completion of this group is a quotient of the fundamental group of this algebraic surface. But if there is any complex analog, or like what is the fundamental group of this algebraic surface, I have no idea. I just what one can say, that if you take the profinite completion of this group, then it's a quotient of the algebraic fundamental group. Yes, and now I think I talked enough about the construction that I can go to the next step to talk about covers. Yes, because like also analogy with this, what people usually do, they take some graph or surface and then they look at covers of this object. So what happens in this situation? So technically it's a bit more difficult to look at covers because even there are such examples where your polyhedra don't have covers at all. So of course with triangles it's more difficult to prove. There are many candidates where it looked like they don't have finite covers, but no one can prove. But if one look,
No finite cover. Finite.
yes, no finite, of course, no finite. But it's another interesting question that about groups which come from really Euclidean buildings. About them is known that they are so-called just infinite. They don't have infinite covers. They cannot have, for example, it's true in the Mumford case as well that this group doesn't have infinite normal subgroups of infinite index. All normal subgroups are of finite index and all have finite abelianizations. So if I have time, I can talk about this. It's just kind of nice facts which are really completely different from like dimensionless. Yes, because of course if you have a surface group, yes, it has a lot of subgroups and so on. But of course here they don't have normal subgroups of infinite index. But this is known fact. This is for classical buildings. It can be obtained from one of Margulis' rigidity results, and there are people who claimed it in more general context. But it's basically, but in Euclidean case. But still, like as I said, that there are examples for obtained from squares, where it's known that the fundamental groups are just simple groups. So it's just to show that in general it's a difficult question to find your covers. And first I was hesitating to give my original motivation or not, but now I see that I have enough of time. I can have some, like maybe 10 minutes. Just stop me if it's really completely boring. But it's another question. I don't know. Maybe there is some algebraic meaning of this thing as well, because who knows? So there are some graphs which are, so now it's really unrelated. A couple of slides which are almost unrelated to the, at least this slide is unrelated to the topic of our program. So some graphs which are called expander graphs, and again, if you don't want to read the definition, it's what is the motivation to look at such graphs. Like the motivation comes from computer science of building networks and okay, like there are really a lot of applications. First I didn't believe, I thought that people maybe just speculate, but since I am interested in expanders, I was really talking to computer scientists. They are really interested in some new constructions of such graphs. And these are the graphs which are in the same time are sparse and highly connected. Okay, so they have to, and this is how one formalizes this. One just defines such combinatorial Tiger constant. Yes, which is so you have somehow you have your set, then you have the set S, then you have the complement of this set S, and so what is this E? It's some kind of boundary. Yes, it's edges which have one end in the set and another end in its complement. And then we just take minimum divided by the of the boundary divided by the size of the set. Yes, and of course we consider such sets which are less or equal than 1/2. And then of course this expander graphs, it has to be an infinite family. That of course if your family is finite, you can always find such epsilon. But this is the trick, that to have such an epsilon for an infinite family, that this Chigger constant is uniformly bounded. And another interpretation, it's really equivalent, that you can just take the eigenvalues of the incidence matrices of graphs, and if like the smallest positive eigenvalue is bounded from below by some constant, it's exactly the same.
What's the question then?
It's to find, no, this is a definition of course, but to find, you see this infinite family of expander graphs,
For
like
example,
really to find.
For example, if we consider all complete graphs with this one.
They're not K-regular for a fixed state.
They are not K-regular.
Ah,
They also have to be K, yes, they have to be also K-regular. K is fixed. And it really looks quite simple, but it turns out to be a very, very difficult question. So first examples which are mathematical examples due to Margulis in the beginning of 70s, and it really involves some non-trivial analysis. So, and this is one of the families which we constructed with Norbert Paringhoff. It's like Kelly graphs of some finite groups. Do I need to define a Kelly graph? Okay, yes, so what is the Kelly graph of a group? It's just for every element of a group, you have a vertex. And there is an edge between two elements if one can pass from one to another by multiplying it by some generator of the group. So, and so this is one of the ways to look at expanders, to construct them as Kelly graphs of some finite groups. And in this case, what is the minimal degree? So of course, if you look at expander graphs, if we want this graph to be sparse, yes? So what is the minimal degree? Of course, it's 3, but if you want to look at the Kelly graphs, so then it's 4, because your non-trivial group has to have at least 2 generators and 2 inverses, yes? Because in your Kelly graph always you have generators and inverses of these generators. So here we have like Kelly graphs of groups with just two generators and 4 relations. So this is maybe like kind of minimal which one could get in such a way, that just two generators and 4 relations. Okay, and then what those groups have to do with what I was talking before, that they are really deck transformation groups. If we have, like, so, just not to the, so if we have this polyhedron, yes, again, like every word here, we write on the boundary of a triangle. Okay, and so here there are 14 triangles. Then for this particular example, there is an infinite family of 2 covers. Okay, so like really in every step, for every power of 2, we can get covers, and those groups are deck transformation groups of those covers. Okay, and the graphs, those expanders, yeah, those graphs, they are kind of one-dimensional skeletons of those polyhedra. So you have kind of tower of polyhedra, and you have there one skeletons, which are those expander graphs. But how it's related to algebra? That in fact, for this tower, in each step, one can really apply this construction, this general construction of Mumford, that in every step there is algebraic surface, and it's really proper cover that all the axioms. Okay, it's just I didn't manage to get it, but usually those expander graphs, they are difficult to draw, like. But in our construction, even one can get a graph with 32 vertices. Okay, but then let's discuss again something which is more algebraic. We can look at the Pro2 completion of our group. So if you see, okay, like this I presented as finite groups, but in fact we have three relations, R1, R2, R3, and those are relations for an infinite group. This is this group, the group defined by those relations is exactly a fundamental group of CW complex, which I showed before. Okay, so we again come back to our original motivation. We have a CW complex with some fundamental group, and so here the way to get finite covers, we just add one more relation. And if we forget this relation, okay, now we are not somehow, maybe we are really not interested how exactly those covers look like. We just know that they exist, yes? So we just take those three relations and look at this group. And not just at the group, but at its Pro2 completion. So, and it's kind of strange from the point of view of Pro-P groups. For example, it behaves as finite group. It satisfies the Golod-Shafarevich inequality. So I, it's a number of relations, and X, it's number of generators. So X is equal to 2. Yes, we have just two generators. 2 square 4 divided by 4, it's 1. So it's kind of, it's even very easy to prove this inequality because the left-hand side is 1, and our group is not free for sure because it has, for example, finite abelianization. So it has at least one relation, even if this R1, R2, R3 is not a minimal. Usually in group theory it's difficult to prove that some system of relations, it's really the minimal system of relations. But since we know that the group G is not free because it has a finite abelianization, for example, so then it has to be at least one relation. So this inequality is satisfied. But as I said, that it behaves as a finite group, but nevertheless the group is infinite by many reasons. And okay, you can just skip those. It's in theory of Pro-P groups. There are different notions of groups for which it was known that they also behave as finite group, those p-adic analytic and lambda perfect, but this group is neither of it as well. And what is kind of also for me it was interesting to find out, and what is also a difference with like low dimensional case, that this group contains abstract free group, non-abelian abstract free group, but doesn't contain free Pro-P group. Okay, in our case it would be 2 group. It doesn't, it cannot contain free Pro-P group. So, but as I said that I don't know yet for sure what is the relation with these algebraic fundamental groups of if it's really the same as the algebraic fundamental group of those Mumford surfaces, but at least one can claim that this group is a quotient of this algebraic fundamental group. No, okay, it's something, again, I don't know, it's somehow, I wrote it as a conjecture, but in fact it's really very, very difficult exercise on linear algebra. And and I think that it's really true. And somehow I don't know exactly, again, what is the relation to algebra, but this group, but also we have many other examples of this kind, have quite nicely structured lower central series. So again, I don't know if there is any kind of algebraic interpretation of this, but it's really, if you take the lower central series of group G, so I really defined it. Yes, you take first commutator subgroup, then you take this gamma commutator subgroup with G and so on. Yes, and then you look at those. Why? I don't know this. Okay, it appeared again. So if you look at those quotients, yes, in the lower central series, then the ranks are like kind of 3, 3, 2. 3, 3, 2. They have, of course, there are examples of such groups of finite widths, but usually it's some big algebraic groups. And for a discrete group, which is not that big, it's kind of strange behavior to have those lower central series. Okay. And now I will talk about something which is not, which doesn't have for sure algebraic analogy, because everything about what I was talking before was coming from classical Brouattis buildings. That's why, like, because of this Mumford's construction of algebraic surfaces, always there was an algebraic surface behind this. But the question is, what if we just go outside, just a little bit outside of this classical construction of finite projective planes as links and so on? So what if instead of link this one vertex, again, we can have some set of triangles, but instead of finite projective plane, we have generalized quadrangle. It's a graph of diameter 4 and girth 8. Okay, there is a picture I can show you, but just, okay, I didn't want to overload it with pictures. So, and then also one can get similar examples. So it turned out technically more complicated. It even somehow solves some questions from group theory. Okay, I also don't want to overload with notations and so on, but it exists. So we can get. So there are two constructions here. So we can have like 15 hyperbolic triangles, 15 equilateral hyperbolic triangles with angles pi by 4, then to write some words on the boundary, and we get one link, and the link at this vertex is generalized quadrangle. Then the universal cover is a building, but it's a hyperbolic building. And also what happened, the abelianization of the fundamental group of these polyhedroids, finite, and so on. But then when we try to look for some covers, the situation is completely different. So, for example, for this group T1, we have the commutator subgroup which has index 9 in the original group, and it's already perfect. And it doesn't seem to have any subgroups of finite index at all until all modern computers allow to do this. So just it doesn't seem to have any, but of course, like, we cannot claim that it doesn't have any because computers didn't find it. But the question is, of course, kind of a dream to find, nevertheless, some algebraic surface. It's maybe still there is some way to generalize this construction of Mumford, because it's really, what is the difference in, like, in Mumford's construction there are Euclidean planes tessellated by triangles with angles pi by 3, yes, but here it's like we just have equilateral triangles with angles pi by 4 and graphs which look almost the same but just a little bit different. And the question if really one can generalize it to some algebraic side. And what would be great if you find some algebraic object, show that its fundamental group is trivial or finite or whatever, and from that fact it would follow that those groups are not residually finite. And this, of course, like in geometric theory, but even maybe in geometry, like Gromov-like geometry, it's already a long-standing question if one can find a hyperbolic group which is not residually finite. So these groups are hyperbolic, and they are kind of strange in between Euclidean and hyperbolic. It was also a kind of long-standing question if one can find a hyperbolic group which is torsion-free and has so-called property T in the same time. And there was some kind of random argument of Gromov that it exists, but there was no, like, explicit example. So to my knowledge, this is kind of first explicit examples of such groups. But they also kind of candidates for different several problems to be counterexamples. But it's kind of difficult to prove. So, but here, what is in the context of this program? Of course, if one would come up with some algebraic structure with finite fundamental group, or which would say maybe some, because I think in algebraic geometry there are such examples of some varieties with fundamental groups which are not residually finite. Yes, so that's why it would be really great. So I think I can stop.
Simply extend the graphs.
Yes.
Is there not a kind must they not come somehow all from some algebraic construction? The algebraic constructions are completely perpendicular on the
You don't understand what is the algebraic structure. So in general, in our construction, what is?
So I suppose that if you just start with some graph, then
Yes.
you cannot find a family in which it will fit in some way and such that the family is. So these are very special objects, yes, the extender.
Yes, it's very special object, and this is one of the ways to find this. The group, if we have an infinite group, if infinite finally generated group with property T, and it's residually finite, then we know that the Kelly graphs of the quotients are expander graphs. But in fact, it's even easy to explain in combinatorial terms what is the property T's, or I'm not going to give like analytic definition, but analogy in this context, that if in those constructions which I explained, if we have a polyhedron with triangular faces, this is important to have triangular faces, and all links which are generalized polygons, which I also defined, then the fundamental group has property T. And then if we manage to have such group with property T to be residually finite, then we have, in theory, we have these Kelly graphs as expander graphs. But what is the problem? That there are a lot of constructions of groups which are, for example, for which is known that there are infinitely many quotients, but usually those groups have many relations. Like there are such pro-P constructions. I think there was, before us, there was someone looked at pro-P groups, because P groups are very nice and easy to handle in terms of Kelly graphs and any other, but those examples had, I think, something like 47 generators and 49 relations, something of this kind. So, because I said that it's exactly for the same reasons how people were proving before that, saying for pro-P groups, it's wrong way. How people were proving that groups are infinite. Exactly, if this inequality is not satisfied, yes, if it another direction, then it's known that the group is infinite. But the problem is, if you try to combine this property T together with Golod-Shafarevich condition, you get at least something, I think, 47 generators. So it's, if you really then want your base group is quite complicated, and if you try to look at the structure of quotient, it's quite difficult. And if you really want to do something practical with these quotients, they have to look somehow nice. And here we just add just one relation, and why it's possible, why we know that those groups, yes, that they are finite, just because of this condition that the original group is just infinite. So we know that they are all finite, but then what was the main technical difficulty is to show, okay, we know that they are finite, but why the order increases? Yes, why it's really infinite. So this was like neither arguments from geometric group theory didn't work and so on. We really had to find some representation of this group and to work with matrices, like really honestly.
So, but these groups are all quotients of
this group is this, yes, so this group is, yes, because we just had one more relation. We have those three relations of this of one group with property T.
And this group residually finite.
Yes, this one is residually finite. To find expanders, it's good to have.
Yeah, exactly. Is this then, no, okay, so maybe you already done. Is this then the fundamental group of something?
Yes.
This is the fundamental group
Of this.
no, exactly this one. So is it not so that the expanders always have a fundamental, in some sense, are close to be fundamental groups of something?
So I think all known constructions, even if they come from algebra, yes, they can also, people have different, very often they have this, that they come from property T. But there are some independent constructions as well.
You mean the fundamental group of something?
It can be interpreted a lot of, because, for example, yes, no, I know what the question comes from. For example, if you have some lattice in saying PGL 3K, yes, you can always get some series of expander in such a way that you just take the corresponding building, you can take the quotient. It's very often has some nice structure. So okay, maybe there are some degenerations, but
But I'm confused. I thought if you want any algebraic variety at all, can't you always put any kind of
For every, for arbitrary topological, for nice topological spaces, yes, but the question is whether you can get it as.
For any.
Yeah, but not for algebraic. Get it for algebraic variety if you don't wish.
No, this is a very interesting question. What would be, because so on the algebra side, I understand on little bit only this Mumford surfaces, which come like really from classical buildings. But as I said, you go a little bit outside of this construction, then what happens? Of course, I was planning to give more examples, but I think just because one can generalize it in different ways. We can also not look at triangles. We can look at polygons with any number of sides and any links. Just the question when there is something algebraically interesting.
By the way, what higher dimension than surfaces?
Yes. What we discussed before? Yes. What is really interesting to look at?
I have a question. Have you tried to write those relations R1, R2, R3 in terms, say, of Lie basis of this group? X, Y, commutative X, Y.
Ah, yes. Yes, of course.
You tried.
One can I can show you that it's really one can do this very easily. They really like in this Koch book.
You can apply the links construction when you put in closure. What the limit explain this is.
Yes, but then what do you have? How you prove that it's true that one can look at the lower central series of this group and it has like really some rigid structure. But the question is how you prove that it's really infinite and then it really exists. Still one needs some independent proof. As soon as you have it, you can look at it, but how you would... No, interesting if there is any independent proof. What we saw yesterday, if you just from generators in relation can go to this, but no, it's of course very interesting to understand.
The question